So much could have gone wrong with this mission, but the fact that nothing did made us ecstatic. The universe, with its vast and infinite expanse, has always held secrets beyond our wildest imaginations. Yet, it seems to be preventing people from sharing information, which is one of the most crucial aspects of science. Suddenly, the most advanced telescopes in history detected something that defies all logic, a cosmic mystery that has left scientists around the world in disbelief. The findings of the James Webb Space Telescope have cast doubt on the Big Bang Theory. Joe Rogan delves into the latest discoveries made by the Webb Telescope, where an astonishing 900 trillion stars have seemingly vanished from existence. She stays up late at night wondering if everything we know is turning out to be false based on the James Webb findings. NASA's $10 billion James Webb Space Telescope has been in space for just over 2 years, but the stunning results it has already produced prove it was worth every penny. The first priority is hardly ever to discover something entirely new. Rather, it's to deepen our understanding of the universe by improving on what we already know. Historically, our most profound views of deep space came from the Hubble Space Telescope. However, as of July 2022, James Webb has taken us beyond what anything else has seen. It is looking for very long wavelengths coming from galaxies that are very far away. The James Webb Telescope has been able to detect extremely long wavelength radiation, wavelengths that are outside the visible range. I call it ultra-red shifted, from the faintest galaxies to the richest clusters, from mostly empty cosmic voids to the deepest depths of far-off space, and much more. The superior telescope has revealed details we've never seen before, surpassing all expectations. When James Webb focused on large regions of space that appeared blank to Hubble, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and the situation is becoming scarier by the minute. What happened? Where did the stars go? How did they disappear without a trace? First of all, it's important to know that James Webb outperformed Hubble by more than we expected. When comparing the capabilities of James Webb and Hubble side by side, you would expect our newest space telescope to do much more in less time. While Hubble has a primary mirror that is 2.4 meters across, Webb's segmented mirror spans 6.5 meters. This leads to a resolution that is 270% sharper for the same wavelength of light and a light-gathering power that is 730% greater than Hubble's. Based on the physics of optics alone, James Webb should be that much better and faster than Hubble, not to mention the additional advantages Webb possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you would expect James Webb to collect 730% as much light as Hubble. However, as you can see from the comparison of its composite image of galaxy cluster SMACS J0723 with that of Hubble, Webb is doing even better than that. Hubble's time is divided into orbits. From its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits for optical wavelengths and 2 for infrared wavelengths were used to make the Hubble composite. Based on simple math, you would expect 6 orbits multiplied by 96 minutes per orbit to equal 9.6 hours, or 576 minutes of Hubble time. But only a total of 3.4 hours, or 203 minutes of Hubble data, went into these images, despite nearly 3 times as much Hubble time being devoted to this target. In comparison, James Webb observed this target for 12.5 hours and obtained 12.5 hours worth of data. The difference lies in their location. Because Hubble is in orbit around Earth, it spends more than 50% of its time with Earth and the Earth's atmosphere in the way of its desired target, and can only acquire useful data when its target is in full unobstructed view. Meanwhile, James Webb is some 1.5 million kilometers away at the L2 Lagrange point. It always faces away from the Sun, Earth, and the Moon, so it never has to contend with these obstacles to pristine observation. Thus, its observations of targets are 100% time efficient, unlike Hubble, which was less than 50% time efficient. This improved efficiency extends to all observations made with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find objects that appeared blank to Hubble's eyes, but in many cases, it can also resolve them and examine their properties, whereas Hubble could not even see them. This helps achieve one of James Webb's main science goals: to teach us in the greatest detail possible how the universe around us evolved and came to be the way it is today. For instance, nearby Jupiter appears as never before, with its bands, rings, auroras, and moons appearing alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging, spectroscopically detecting absorbed and transmitted light that revealed the presence of molecules. Star-forming nebulae display unprecedented details from new, young blue stars to gaseous features. James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly into a 140-plus megapixel view, expansively revealing far-flung galaxies. Just 1% of this view contains 1 to 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Endel, but arguably its greatest images are of individual galaxies. Webb's views reveal gas, dust, stars, and more, with central black holes containing cores shining in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either the stars are still there, still going through their death throes with less luminosity and perhaps obscured by dust, or they just collapsed into black holes without going through a supernova stage. But in the worst-case scenario, the universe is simply disappearing, and we are powerless to stop it. It has been nearly a century since scientists first theorized that the universe is expanding and that the farther away a galaxy is from us, the faster it appears to recede. This isn't because galaxies are physically moving away from us, but because the universe is full of gravitationally bound objects, and the fabric of space that these objects reside in is expanding. However, this picture, which has held sway since the 1920s, has been recently revised. It has only been 20 years since we first realized that this expansion was speeding up, and that as time goes on, individual galaxies will appear to recede from us faster and faster. In time, they will become unreachable, even if we journey toward them at the speed of light. When you look out at a star whose light arrives after traveling toward you for 100 years, you are seeing a star that is 100 light-years away, due to the finite speed of light. But when you look out at a galaxy whose light arrives after traveling toward you for 100 million years, you're not looking at a galaxy that is 100 million light-years distant. Rather, you're seeing a galaxy that is significantly farther away than that. The reason for this is that on the largest scales, objects that aren't gravitationally bound together into galaxies, groups, or clusters are in an expanding universe. The longer it takes a photon to travel from a distant galaxy to your eyes, the greater the role of the universe's expansion, implying that the most distant galaxies are even farther away than the amount of time their light has been traveling. This shows up as a cosmic redshift. Since light is emitted with a particular energy and hence a particular wavelength, we fully expect it to arrive at its destination with a particular wavelength as well. If the fabric of the universe were neither expanding nor contracting but rather constant, that wavelength would remain the same. But if the universe is expanding, the fabric of space stretches, and the wavelength of light becomes longer. The great redshifts we've observed for the most distant galaxies have absolutely verified this picture. But we can do much more than just determine that the universe has expanded and continues to expand. We can use all the information we gather to conclude how the universe has expanded over its history, which in turn tells us what the universe is composed of. Once the light leaves a distant cosmic source, the expanding universe stretches the wavelength of that light. This leads to a redshift where more distant objects will have their light redshifted for longer amounts of time. When different components of the universe were more important, by measuring sources at a range of distances, discovering their redshift, and then either measuring their intrinsic versus apparent size or their intrinsic versus apparent brightness, we can reconstruct the entire expansion history of the universe. Additionally, since the way the universe expands is determined by the various types of matter and energy present within it, we can learn what our universe is made of. 68% dark energy, equivalent to a cosmological constant, 27% dark matter, 4.9% normal protons, neutrons, and electrons matter, 0.1% neutrinos and antineutrinos, about 0.08% photons, and approximately 0.5% all other forms of energy. Yet, despite this, James Webb's observations present us with a cosmic paradox. 900 trillion stars that seem to have vanished. Webb was able to detect these stars and their disappearance due to its impressive ability to peer further back into the universe's past. The two main possibilities for these vanishing stars are either that they are obscured by cosmic dust or collapsed into black holes. No matter how we look at it, the data presented by James Webb forces us to question our understanding of the universe, our models of cosmic expansion, and the very nature of existence itself. We are left with two critical questions. What is causing this unprecedented phenomenon, and how does it align with or challenge our existing theories about the universe? The answers, if they come, may require a complete overhaul of our current scientific models or even a radical rethinking of the universe's fundamental nature. The latest data from the James Webb Space Telescope has sparked a wave of scientific excitement and confusion, particularly regarding the mysterious disappearance of 900 trillion stars. This anomaly has prompted researchers to reevaluate their understanding of cosmic processes and theories. One of the more intriguing aspects of Webb's findings is the unexpected appearance of what are being called cosmic voids on a scale previously unimaginable. These vast expanses of space, which seem devoid of the typical galactic structures one would expect, challenge current models of galaxy formation and distribution. Traditional theories suggest that the universe's large-scale structure should be more homogeneous when viewed over sufficiently large volumes. The sudden visibility of these voids might indicate that our previous models, which largely depended on observations from telescopes like Hubble, were missing key components. In addition to these voids, James Webb's unprecedented resolution has led to new insights into the early stages of galaxy formation. The telescope's ability to observe these primordial galaxies in their infancy offers a glimpse into the conditions that prevailed shortly after the Big Bang. It appears that some of these early galaxies have structures and compositions that were previously theorized but never directly observed. This could imply that our understanding of cosmic evolution needs a fundamental revision. The disappearing stars could also be linked to phenomena involving dark matter and dark energy. Although dark matter has been well documented in terms of its gravitational effects on visible matter, its precise nature remains elusive. The sudden absence of these stars might be a clue indicating interactions between dark matter and regular matter that were not accounted for in existing models. Similarly, dark energy, which is believed to drive the accelerated expansion of the universe, might be interacting with matter in ways that were previously unknown. If these interactions are affecting star populations, it could lead to a deeper understanding of the universe's expansion dynamics. Astrophysicists are also considering the possibility that Webb's findings could lead to the discovery of new types of cosmic events or structures. For instance, the idea that these stars might be part of an unknown phase of stellar evolution could open new avenues of research. It's conceivable that some stars could be undergoing a phase of transformation that is not yet well understood. This might involve new types of stellar remnants or novel forms of stellar death that haven't been observed before. Another angle of investigation is the role of cosmic dust and gas. Webb's advanced infrared capabilities allow it to see through dust clouds that obscure our view in other wavelengths. It's possible that some of these stars have not disappeared but are merely hidden behind dense cosmic dust. If this is the case, then future observations with Webb or other instruments might reveal these hidden stars, resolving the apparent mystery. The implications of these findings extend beyond astronomy and could impact fundamental physics. If the universe is indeed undergoing changes that lead to the disappearance of large numbers of stars, this could affect our understanding of fundamental physical laws. For example, the standard model of particle physics might need to be adjusted to account for new interactions or particles that could be influencing stellar life cycles. Additionally, theories about the fate of the universe might need to be revisited. Current models predicting the universe's ultimate fate, whether it will continue expanding forever, slow down, or eventually collapse, could be profoundly impacted by these new observations. Moreover, the data from James Webb could also have cosmological implications, affecting theories about the universe's structure on the largest scales. The observation of voids and the disappearance of stars might necessitate changes in the way we model cosmic inflation and the distribution of matter. Theories about the multiverse, which suggest the existence of multiple or parallel universes, might also be affected if these findings provide evidence of phenomena that are inconsistent with our current understanding of a single, expanding universe. The role of theoretical physicists and cosmologists will be crucial in interpreting these new observations. Their models and simulations will need to incorporate Webb's data to predict how these new discoveries fit into the larger cosmic framework. Collaborative efforts between astronomers, physicists, and mathematicians will be essential to unraveling the implications of the disappearing stars and other phenomena observed by the telescope. In summary, the latest data from the James Webb Space Telescope is pushing the boundaries of our understanding of the cosmos. The unexpected disappearance of 900 trillion stars is not just a curious anomaly but a potential harbinger of new physics and cosmological insights. As researchers delve into these findings, the scientific community is poised on the brink of possible breakthroughs that could redefine our grasp of the universe and its underlying mechanisms. The coming months and years will likely see intense scrutiny and debate as scientists work to integrate these new observations into our broader understanding of the cosmos.